Hello everyone, hope this video finds you healthy and well and good spirits during these strange times. My name is Logan Nesbitt, and my group with Isaac and Austin, we're going to go through the advanced thermal simulation that SOLIDWORKS has and how to use it. And in order to study it, we thought it'd be a pretty cool idea to try and model a JetBoil and then see what the thermal effects on the burner and the fins and the mug of a JetBoil would look like. So I'm going to walk through our model with you guys, and then Isaac and Austin are going to go through more of the simulation techniques. So first here we have our canister with our fuel, and then we'll go into the burner here. So we decided to make the burner out of aluminum. That's what the JetBoil website said it was made out of. We went with 6064 T6 because that seems to be the aluminum that we always use in our practice problems for all of our classes. So we went with that one. And then here are the fins. Now the fins are a little different from the actual fins. The actual fins kind of have this like zigzag up and down, like accordion shape, but we decided to do it this way. It's a lot easier, and we didn't think that it would really affect the results a whole lot. And then the next we have our mug. Now this is where our biggest difference is. The mug of a real JetBoil has aluminum with a plastic coating all over the outside. What we could not figure out is if the aluminum was just in the base to help the heat transfer into the liquid, or if the entire mug was aluminum covered with that plastic on the outside. So for simplicity, we just made the entire thing out of this plastic, and kind of hope the plastic is the similar one that they use. But yeah, so that's our main difference there. And then we have our lid, of course. But yeah, that's our basic JetBoil model, and then we'll go over here to simulation, study, and then over here to the left you'll see down here we have under advanced simulation we have thermal, and I'll leave Isaac and Austin to show you guys what that's all about.
So we're going to use a thermal simulation in order to model the heat coming out of our burner. Very similar to the force simulations used previously. Start off in the add-ins, make sure to have the simulations add-in. And then you're going to start off in the simulation tab, hit new study, let it think for a second. And we're going to have this window pop up. Previously we've used just a general static simulation. Down here in advanced we have options for thermal. Also a 2D option, but since it's a relatively complex 3D model, I'm going to go ahead and leave that unchecked. Go ahead and hit the green check mark. So once SOLIDWORKS finishes thinking, we get just kind of a basic little screen here with some options for our thermal simulation. We want to make sure that all of the parts have defined material. So we've got aluminum and steel for the fuel canister. Material is important just so SOLIDWORKS knows the thermal coefficients that it's going to be using. Once you're ready to actually start the simulation, we have options for all the thermal loads. Right click on the thermal loads, you get temperature, convection, etc. So in the temperature, you're able to choose starting surface temperature and the surface temperatures that you're going to want if you want to hold a temperature constant. And then you've got some heat transfer choices, convection, if you just want to have free convection, heat flux, if you have a known flux, and then heat power and radiation. Heat power is going to be your generation, so this is what we're going to be using for the burner that we're using. And then we don't have any conduction components here, but if you're going to study some thermal conduction, you have options for contact, so you can choose bonded or insulated for two surfaces that are touching, and then in there you're able to measure and edit what sort of thermal resistance there is between the two surfaces. Since we're not using any conductive heat sinks, we're not going to use this option. And then since this is a free open system, we're going to want to make sure to use convection on the entire surface. So even though we have the generation from the center of the burner, we're also going to have convection just with the atmosphere. So we would make sure to go into thermal loads, give it convection, and just have all the open exposed surfaces have a convection heat transfer, and then make sure to choose a convection coefficient that's accurate for the gas that it's exposed to. So with all those options, we're able to run our thermal analysis of our little burner stove.
In order to do a thermal analysis on our JetBoil model, we needed to heavily simplify the simulation. While a flow analysis using fuel flow parameters might have provided a more accurate simulation, it was extremely difficult to find any specifications as far as the gas flow rates of the fuel, and our model was designed in a simplified state. Using the thermal analysis simulation as shown earlier, specifications were chosen in order to model the analysis. A transient analysis was chosen with a total time of 60 seconds, as this would provide the burner adequate time to heat up the JetBoil and provide a water boiling time of around 100 seconds as stated on JetBoil's website. Next, for connection components, the entire assembly had a global contact connection applied to it, where each part is connected by a mate in the assembly. This allows a mesh to be created. Next, the mesh was created with the mesh size set to fine. After, thermal loads are applied to simulate the fuel burning as it flows from the burner. A 0.35 BTU per second heat power was applied to the top surface of the burner. You can kind of see it. I'll hide this bad boy for a second. It was applied right there. Okay. Next, an initial temperature of 60 degrees Fahrenheit was applied to all parts of the assembly. A convection load was applied to all exterior exposed faces of the JetBoil assembly with a convection coefficient of 35 watts per meter squared Kelvin and an ambient temperature of 60 degrees, seen right here. To simulate the heat transfer of the flame as the burner continues to output heat, a convection load was applied to the interior of the JetBoil, to the inside faces of the fins, and the bottom surface of the pot, which would be exposed to the flame. A convection coefficient of 150 watts per meter squared Kelvin was used, along with an ambient flame temperature of 600 degrees Fahrenheit, which was chosen as a good approximate for average flame temperature inside of the apparatus. Go and re-show the mug. With all these thermal loads defined, the simulation can be run. It is calculating each time step of 5 seconds up to a minute, which will be 12 iterations. Here are the results. This is running with the fins that are an integral part of the JetBoil. The results are shown as a temperature plot, and in the plot tools, a section clipping was used to display a cross section of the JetBoil to get an accurate temperature distribution on the inside. After 60 seconds, the burner had gotten to the temperature of 1064 degrees Fahrenheit, right below its melting point. In real life, the burning gas would be outputting this heat, not the burner itself, so this is merely a consequence of the simplification. The bottom of the pot, which would be boiling the water, as seen right here, reaches temperatures of up to 562 degrees Fahrenheit, which provide a good heat to boil the water. To better see the transient process, an animation plot tool is used. It is extremely finicky, but shows heat transfer extremely well. Sometimes it fails, sometimes it doesn't. Hopefully it doesn't fail this time. Cool, looks like it's working. So it's calculating and then it will run the animation. So it's really cool because it shows a full temperature distribution with the final temperature, so you can see how heat transfers. Goes from the burner, goes along the fins and up towards the bottom of the pot, and provides just a really sweet visualization. Just like that. Cool. So, to see how effective the fins are for efficiently transferring heat to boil the water, the same exact simulation was set up with the fins suppressed. This required a different configuration. So, we will go to the results using the same heat power as before without fins to model a possible competitor's backpacking stove. Here are the results. Okay, as seen, the burner reaches a higher temp, which is 1238 degrees Fahrenheit, which is higher than the melting point of its material. This isn't entirely accurate, but shows that competitor stoves can't use the same high heat power without using fins as a heat transfer mechanism to prevent the material from melting. And then here's an animation of this one. And then with this one, without the fins, you can kind of see how it differs. The heat transfer goes from the burner, kind of goes to the bottom of the burner and the sides of the mug, and then slowly goes up. There's some convective heat transfer to the top of the mug, but it doesn't do as great of a job as if there were fins. The final simulation is another setup, but with a heat power of 0.25 BTUs per second instead of 0.35 BTUs per second to show a competitor backpacking stove in operation without reaching its melting point, which are shown in the results right here. Also shown in these results is that the bottom of the pot is at a lower temperature than the JetBoil with its fins, which is around 291 degrees Fahrenheit right here. So it'll take this stove longer to boil water than the JetBoil. Here is the animation from this one, which is very similar to the previous one, just at a little lower temperature. All in all, I would recommend using thermal analysis for more basic simulation needs, as it is quite tricky to use for a simulation such as this one. And as stated before, a flow analysis would be more accurate, but way more complicated, especially attempting to approximate the boiling of water inside of the mug, as SolidWorks is unable to process state changes of fluids. Thanks for watching.